Edexcel Core Pure, second order differential equations 1, the homogeneous case. Auxiliary equation method for second order differential equations. So now we're going to look at second order differential equations in more detail. So these will have the highest power in them of d2y by dx squared. We will also be considering linear second order equations, and this means that we do not have any other powers on our derivatives other than 1. So for example, d2y by dx squared would be linear, but dy by dx cubed would be nonlinear, and therefore this differential equation is not linear, and therefore we would not be looking at methods to solve this nonlinear differential equation. So here is a second order linear homogeneous equation. Remember, it's homogeneous because it adds up to 0, equals 0 on the right hand side, and I am going to try y equals a e to the mx as my general solution. And if I differentiate this once, I get a m e to the mx, and I differentiate that again, I get a m squared e to the mx. If I sub all this into a differential equation, my second order differential equation, I get am squared e to the mx plus twice the first derivative minus 15y, and it must add up to 0. It's worth noting that a e to the mx will cancel out, and we'll be left with m squared plus 2m minus 15 equals 0, which is the auxiliary equation, or I'm going to call that the AE, the auxiliary equation. Now, lots of students and teachers miss out that line of working and perhaps don't always mention the first and second derivatives. It's good to see all of that, but as a minimum I recommend writing down y equals ae to the mx before you write down your auxiliary equation, so at least we know what m represents. This quadratic equation in this case factorises, and we get two real distinct solutions for m. M is 3, m is minus 5, and from those two solutions for m we can write down that y could be a e to the 3x, or y could be b e to the minus 5x. And to get the complete general case, we need to include both options in our general solution. So this is the GS, the general solution. Notice the general solution contains two arbitrary constants, a and b, because we started off with a second order differential equation at the beginning. And a useful thing for you to practice here is to take this general solution, differentiate it 2 times, and sub it into the left hand side of this differential equation to see if the left hand side adds up to 0 as required. So you could verify the solution works. It's a good thing to practice. So just to summarise, we're going to take this homogeneous equation that equals 0, and we should mention that y equals ae to the mx. That's where the m is coming from. But always write down your auxiliary equation, which should be a quadratic in m if it's second order. Here we've solved for m and got two real distinct solutions, and that has allowed us to write down the general solution. And again, the general solution contains two arbitrary constants, a and b, because the second order equation must contain two constants in the general solution. We'll now look at this in a little bit more detail using a GeoGebra file. So here we are looking at the solution where I've set the constants a and b both equal to 1. We can see the solution on the right. Notice the y-intercept is 2 because when x is 0, y will equal a plus b. So that's why we're getting 1 plus 1 is 2. And if I change the values of a or b, then the y-intercept will be a plus b. A couple of other things to notice here. If I set, for example, a equal to 0, and start to vary b, we can see that the y-intercept is the b value, and as x gets bigger and bigger, this exponential will decay towards 0, and therefore we can see y getting closer to 0. When x is negative, this e to the minus 5x will get bigger and bigger, and we can see y getting closer to infinity when x is negative. If I make a bigger and set b equal to 0, we can see again the y-intercept is a, and now when x is positive, we can see that this bit is obviously 0, and e to the 3x will get bigger and bigger, and e to the 3x when x is negative will decay towards 0. So we can, by controlling a and b, we can determine the kind of solution we will get to the second order differential equation. And we will look at how we can find a and b in future videos. So to generalise what we've seen so far, we've looked at a second order differential equation, and we looked at the case where the auxiliary equation had two distinct real roots, and that was because the discriminant of our auxiliary equation was greater than 0. So that meant we got two distinct real values for m, and here I've called them m is lambda 1, m is lambda 2, and because we've got two real distinct solutions, the general solution is y equals a e to the lambda 1x plus b e to the lambda 2x. Notice the two constants a and b. And we'll be looking at different scenarios for the auxiliary equation in future videos. So in the next video we're going to be looking at finding particular solutions using initial conditions.